So let's play with this on a spreadsheet. So I'm going to double check that the equation given here matches the linear regression equation that either a spreadsheet or stat key would come up with. So I want to highlight the table. And when you highlight information, tabular information from a website like this, you want to make sure you start just at the beginning of the upper left of the table, click and drag and end just at the end of the last thing in the lower right part of the table, and then copy it. And if you copied it right, then you should be able to just paste it directly into the spreadsheet and it should look pretty similar. The next thing I want to do is, let's get rid of that. I want to make the scatter plot. And so I'm going to insert a chart here. And the data was highlighted when I did that. Now here it's making a line chart. That is not what I want. I want a scatter plot. And so I'm going to point to it. I hover over it, it says scatter. And usually it'll get it correct. So it's putting the X values, the first column horizontally, which is correct. And the second column, Y, it's putting vertical. Title's kind of lame, but that's okay. So those are the points there. The scale for the X and Y axis doesn't exactly match what was in the homework problem. And it's a little, the scale is a little bit different. So, but it looks pretty similar to what's there. Right? This one is just longer horizontally. The next thing I want to do is get the equation. So there's a quick way to get the equation. And the way to do that is customize. The series is the data. And if you scroll down in the series section in Google, you'll see that there's a trend line option. So that'll put a line in there. So this is what's called the linear regression line. If I scroll down a little further, once I hit trend line, I have the option for a label, and I want to use the equation. So this is the quickest way to get a linear regression equation on a spreadsheet. So you highlight your two quantitative variables and their values, and you make a chart. The chart should be a scatter plot. Then you customize the series to show a trend line and label using the equation. The downside of this is sometimes I need more decimal places than the spreadsheet gives there, but that should pretty closely match what was in my problem. So 2.98, 40.3, 2.98, 40.3. Okay, perfectly matches. And again, the difference will be the number of decimal places. Suppose you were asked for more decimal places, then you have to do an additional step. So I'm going to just move the chart out of the way a little bit, and I'm going to make a place here for some summary statistics. And the summary statistics I want are the slope, the intercept, sometimes we call it M and B, but I also want the correlation coefficient. So I'm just going to call that core coefficient. And the formulas for those are pretty straightforward. Slope. Notice here it wants the Y data first and the X data second. That's super important. If you mix that up, you'll get the wrong slope. So watch. If I select X first, comma, and then Y second, and hit enter, it's not the number I see here. 0.281, 2.98. So I got my X and Y backwards. See, definitely important you pay attention to that detail. It's got to be Y data first. The title doesn't matter. You can select it or not, comma, X data second.
Thank you.
Yeah. And then intercept is similar. The order matters. So just start typing intercept, and it's just called intercept. And it's got to be Y data first. And here I won't select the title. And if you don't select the title for Y, don't select it for X, otherwise the computer will get confused, and then close your parentheses. And then the correlation coefficient. So again, I'm doing this just in case I needed more decimal points than what the graph gives. The graph doesn't ever give the correlation coefficient. We have to calculate that separate. So I start typing correlation, and I can see there's a function called correl, which is the Pearson product moment correlation coefficient. That's the one we want. So I'm going to select it. And again, Y data first, X data second. And there are a couple of questions where or the computer asks you for a slope. Sometimes the graph has enough decimal places for the problem you're given. Sometimes it doesn't. So if you need more decimal places than the graph gave, then you'll have to calculate it separately there. All right, so there's the correlation coefficient. So again, this has it's uphill, right? Positive correlation. The points relatively line up, so we're going to get something closer to 1 than 0. So here my correlation coefficient is 0.9. Now I want to show you something else that often people get confused about. When I was in the edit section under customize series, underneath use equation, it said show R squared. R squared is not the same thing as R because they take that number and they multiply it by itself, which gives you a totally new number. It is a useful number in statistics, but we're not covering it in this course. So if I do select R squared, notice it's 0.839. It's not the number here. So in this particular class, we are not going to use R squared. It's called the coefficient of variation. It is useful, but again, if you take another class in statistics, you might use it there, but we're not going to get to it in this class. So just beware of that right there. All right, so as far as linear regression, scatter plots, what we just did right here is pretty much technically everything you need to know how to do for the problems that we're working with. Let's see. Oh, there is one other note I want to make. Why bother making a line and getting an equation here? Well, the reason we would bother is if we think this is reliable data here, well, then we might want to use it to make predictions. Now, nobody in this particular group spent 9 hours per week. We're wondering if somebody did spend 9 hours per week, about what would their grade be? Well, we can use this equation here to predict that. So in terms of why we bother with linear regression and scatter plots, it's to make predictions. And the predictions are going to come in two different ways. One way is we look within the data that's given. So here we have students that spent between 6 and 20 hours per week studying, and we want to be able to predict their grade. Nobody in this particular data set spent 9 hours or say 16 hours. We want to know, well, what if they did? So if I make a prediction for something like X equals 9, then I would use the equation to tell me what Y should be, the grade. So to make that happen here, I would do something like type equals, and then I'm just going to use the numbers in the chart below. It says use the number 2.98, multiply that by the X value that we have here to the left. So I'm just going to click on it. And then I want to add on what I believe to be the y-intercept, which I'm just going to type it, 40.3. So according, ooh, something went wrong there.
Sorry, you had put a 9 in front instead of the
Oh,
2.
instead of a 2, thank you. Yeah, I knew something was not right. Okay, there we go. So this predicts if this is reliable data over here, if somebody spent 9 hours per week studying, we would expect their grade to be about a 67. Let's suppose somebody spent more than 20 hours studying, right? That's outside of our data range, or maybe less than 6 hours. So let's go with, actually, let's go less than 6 hours. Suppose somebody only spent 4 hours per week studying. Then using that same idea, we would say, all right, take the 2.98, multiply that by the X value 4 we just picked, add on the intercept, 40.3, and here we would expect their grade to be 52. Now, note, the 9 for the X is within the given numbers, right? The given numbers range from 6 to 20. 9 is inside the range of numbers from 6 to 20. When we pick a number for X that's within the given set of X values from lowest to highest, that's called an interpolation. When we pick a number that's outside of the given numbers, so for example, again here, the min is 6, the max is 20. So if you pick a number and an hours per week less than 6 or greater than 20, that's outside of the data that we know, that's called an extrapolation. And the general rule in using models like this, model being the equation that we found, is that if you have a reasonably high correlation coefficient, it is safe to make predictions that are within the given data range. That's called an interpretation. So this is a safe thing to do. If you're using input values that are not within the given range of data, then it's more dangerous to make a prediction. The farther you get from the data set, the more dangerous it is because you don't know, you don't have that data. Now here, my correlation coefficient is pretty high, so I feel pretty safe making an extrapolation on 4. So I'm going to say relatively safe. But again, there are limits to that, and it's hard to measure the limits as to how far you can go below or above. But the farther you go away from the given range of data, the sketchier your prediction is, especially if you don't have a high correlation coefficient. So that's another big idea here. All right,
That's
and I
so
think,
cool. Thank you.
yeah, so that pretty much summarizes section 2.5 and 2.6.
Oh, wow.